Okay, we're going to be looking at RC circuits, mainly the charging of a capacitor. It'll be a combination of a switch, an EMF, a resistor, and a capacitor. This is prototype 14, physics 252. I show here the circuit, and I label the EMF, switch 1 and switch 2, the resistor, and the capacitor C. Now in a previous video, we talked about a discharging capacitor. So I suggest that before you look at this one, you look at the ideas we talk about in the discharging capacitor. Notice that I also label each of the vertices A, B, C, D, and each of the nodes E and F. We're going to give values R equal 1 kiloohm, C equal 1.5 times 10 to the third microfarad, EMF equal to 10 volts. That gives an RC time constant tau equal to 1.5 seconds. Now take a minute, pause the video, and describe what happens when S1 is closed. Well, when you close S1, immediately a current starts to flow, and that current will be equal to EMF divided by R, because the capacitor is initially uncharged, and that's where you get, and there's no potential drop or no potential difference across the capacitor. Initially, at the instant that switch is closed, the whole potential drop is across the resistor. As the charge continues to build on the capacitor, the potential difference across the capacitor increases and the potential difference across the resistor decreases. Now, let's apply Kirchhoff's loop law to the circuit, going around the path A, B, C, D, and back to A. Once again, pause the video and try to obtain Kirchhoff's loop law. Well, that gives us the equation, the EMF minus the potential drop or potential difference across the resistor minus the potential difference across the capacitor must equal 0. Now, how is I related to Q? Well, of course, the time rate of change of charge is equal to the current. So dq dt equals current I. Now let's write the equation above in terms of Q only. Go ahead, pause the video, and try it. And we have that the EMF minus dq dt R minus Q over C is equal to 0. Now let's recall that when we looked at the discharging capacitor, we obtained Q of T equal to EMF times the capacitance, which is the maximum charge, times the exponent raised to the minus T over RC. In the charging capacitor, the charge is initially 0 when we close S1. Then as time progresses and charge begins to accumulate on the capacitor, it becomes charged to some maximum value. So let's try as a solution to this equation 1 up here, Q of T equal to some A plus B exp to the minus T over RC. At T equals 0, using equation 1, can we get a relation between A and B? Go ahead and try to obtain that relation. Pause the video. Yes, we find out that A has to equal minus B. And so we get for Q of T, A minus A exp to the minus T over RC. Now, can we use another relationship to set what A is? Can we use the fact that as t goes to infinity, Q of t becomes Q max, the maximum charge on the capacitor, which in turn is equal to the EMF times the capacitance. So what is the equation? It is that Q of t is equal to the EMF times the capacitance times 1 minus exp to the minus t over RC. And once again, RC will be 1.5 seconds. EMF times the capacitance will be 1.5 times 10 to the fourth microcoulombs. Now, can you take a moment and pause the video and plot what you think the behavior of the charging capacitor will be? And I show here the charging capacitor. It initially starts with 0 charge on the capacitor, charges up very quickly, and then begins to tail off and slowly approaches the maximum charge given by the EMF times the capacitance. And that is end of prototype.